Okay, so we left off in the last video to talk about how metals lose. So these are metals. Wow, that doesn't look like metals, but that's metals. And non-metals gain. And how many they gain or they lose, depending if they're a metal or not metal, depends on how far away they are from the noble gases. So let's just take a look at sodium plus 1. Now sodium plus 1 is 1s2, 2s2, 2p6, 3s1. But sodium plus 1 means that that 3s1 is lost. It was gone, so it becomes like neon. So again, you should be following along on your periodic table as we talk about this. F negative 1 is also like neon. Now, it's not really neon, of course, right, because the nucleus isn't changed. But to become F minus 1, it just had to gain an electron. It was 2p5, and it gained one to become 2p6, just like neon. Now, when things have the same number of electrons, the same electron configuration, they're said to be isoelectronic. So again, you are definitely going to want to look at the periodic table to see why magnesium forms a +2, a +1, a -1, a -2, and a -3. They all are going to have 10 electrons like neon. Okay. Now, how can we compare the sizes of a isoelectronic species? Well, here's what you need to do. Kind of counterintuitive, but within the group of them, the one that has the most protons is the smallest. And of course, the reason being is that the more protons you have in your nucleus, let's just say you have 8 protons versus somebody who has, I'm just going to say 3 protons, okay? Well, if you are isoelectronic, meaning that you have, 1, 2, 3, 4, 5, 6, let's just say 1, 2, 3, 4, 5, 6. And they each have 6 electrons. Well, think about this. You have negatives on the outside, positives on the inside. This pulling power is going to be a lot greater than this pulling power. So this is really super positive. These electrons are going to be pulled in close. So this will be the smaller thing, the smaller species. Here, the pulling power isn't so great. So yes, it'll attract those electrons, but not to the great extent that all these protons will. So we look at a group of isoelectronic things, and we just look and see who's got the most protons. So I thought there was another slide here, but you basically look at the most protons, and whoever's got the most protons will have the smallest volume. It'll pull it in, and it will be smaller in size. And of course, the thing that has the least number of protons will be the biggest because it can't hold on to those electrons, and they'll spread out, and it'll be bigger. The next topic is periodic properties, and because we talked about these valence electrons, that families have the same number of valence electrons, they behave the same. But they are different too because they are in higher and higher energy levels. So just take a look at the first family, like for instance lithium at 2s1, sodium 3s1, and so on. They're all s1s, absolutely, but they go down to level 7. You get all of these down to level 7, francium, 7s1. Those are in bigger and bigger energy levels. Now, metals like that tend to increase in their property the farther down in the group you go. Nonmetals tend to increase their property the farther up in the group you go. And we're going to talk about that. But sometimes people will say, what's the most reactive element on the table? Well, it really depends. If I'm talking down here, francium is the most reactive metal. But over here, fluorine is the most reactive nonmetal. Now, the noble gases don't count. So most reactive metal, most reactive nonmetal. And we're going to talk about this. This is in level 7 versus lithium in level 2. And so you can kind of see these electrons are farther and farther from the nucleus. They're kind of there for the taking. And so that's why that's so reactive. This is based on how the size of these. Now, please don't mix this up with isoelectronic species and comparing those sizes because this is a different animal altogether. We're not talking about charges here. We're just talking about atoms, no ions. Okay. Now, the atomic size of the atom increases as you go down the table. So again, you should be looking at the periodic table. The size increases. So the biggest atom is down here, the biggest atom. And then the smallest is here. Okay, the smallest is here. And it gets bigger as you go to the left and bigger as you go down. Okay, or conversely, I guess you could start the smallest down here, then so it goes bigger and bigger as you go up into the right. Now, why is that? Well, as you go down, let's tackle this first. As you go down the table, why is the atom getting bigger and bigger? And that's actually really simple. It's just more and more energy levels. Okay, going from energy level 1 to 2 to 3 all the way down to 7. Okay, more complex maybe is why is it decreasing? Why do we get smaller as you go across this way? Okay, why is that you get smaller, and the smallest is over here? By the way, we are going to talk about that as being fluorine. I'm going to leave noble gases out of this whole thing. The smallest over here, fluorine. Why is it that it gets smaller going this way, bigger going that way? Because you are in the same energy level. Okay, so let's say whatever one you want to talk about, n equals 2, for instance. You're in the same energy level going across that period. However, more, but more and more protons pulling in that nucleus. So fluorine has more protons than lithium over here. And so as you go across, it's the same energy level, energy level 2, but more and more protons pulling it in and making it smaller and smaller. All right, so all of the trends are going to be based on the size. So if you get the size down, you're probably fine for everything else. Ionization energy, definition, energy required to remove an electron. So I'm going to try to get an electron away. You have to ask yourself, how hard is it to remove an electron? And the answer is, well, how tightly is it being held? Okay, so think about francium down here at level 7. Now, yes, it has a lot of protons, granted, but that has 7 energy levels. These n equals 7. Huge amount of energy levels. They're going to shield the nucleus and just go way out there. These electrons are out here for the taking. Those electrons in the 7th energy level, it's like taking candy from. They don't feel that pull of the nucleus at all. Well, okay, a little bit, but it's so easy to get those electrons. Now, as you go up higher and higher, you get less and less energy levels up to, energy level 1 even with hydrogen. That's not that many energy levels. It's really close to the nucleus, so those get harder and harder to get. Now, they're not that hard. Metals are pretty easy to get electrons from, but it does get harder and harder and harder. Now, as you go across, it's getting smaller and smaller and smaller, right? Getting smaller as we go up, smaller as we're getting over. And what's happening here is over here with fluorine, you have got only 2 energy levels. And they are actually being held very tightly. Only 2 energy levels, a fair amount of protons. These are being held so tightly. So this has a super high ionization energy. This has a super low ionization energy. This is like taking candy from a baby. Over here, you are not getting that electron. Fluorine doesn't give up electrons. Fluorine takes electrons. So when we talk about metallic character, this is a great metal. It gives up electrons so easily. This, as you head over, it's a trend. Fluorine never becomes a +1. You never see that. You always see F-1. It's going to take them. It's not going to give them away. The energy required to remove that electron is so great that it's just not going to happen. Super high ionization energy, unlike down here where it's, piece of cake. Okay, so what is the trend? Again, what do metals do? Metals give up electrons. So if that's the definition of a metal, then francium is just an amazing metal. So good. Its electrons are in n equals 7. The electrons are there for the taking. It's an amazing metal. As you go up farther and farther, it's going to get harder and harder. I'm not saying they're bad metals, but they're not as good as francium. So as you go up and over, now this is going to be the whole table, so just know this trend, up and over. Over here, fluorine, this is a very bad metal. It's a terrible metal. In fact, it's so bad, It's a nonmetal. Okay, so know the trend there. As you go up the table, you lose a little bit of metallic character. As you go over, you lose a lot of metallic character. But this is the highest metallic character. Call it MC, metallic character. And this is the lowest metallic character. So bad, it's a nonmetal. And of course, non-metallic characters, the trend, of course, is just really bad, low. Okay, this is not a nonmetal. This can't hold on to its own electrons, let alone take somebody else's electrons. But as you go up and as you go over and you get to fluorine, this is the star nonmetal. Okay, it takes electrons, never gives them up, it takes them. And then there's this, this scale, the spectrum from here on up. And you can do this anywhere in the table. All right, so you should look at the trends for all of these. I won't do a synopsis because you could go back and watch the video again. But you should go through and order the following list to largest. Just look at these three, try to do it on your own, and order them from smallest to largest size. Then, smallest to largest ionization energy, smallest to largest metallic character, smallest to largest non-metallic character. And if you spend some time with it, you will start to understand this, learn the trend. Here are the answers. Do it first, check your answers, see how you do.